Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and welcome back to our course. And I hope you are doing well. And in this video, we are going to talk about a new topic, but it's still in the thermodynamic general um, concept, yeah. But we are going to little bit learn specific about something called the thermal behavior of matter, yeah. Okay, so what are we going to learn, yeah, in this chapter, yeah. In this chapter we are going to learn about how material respond, yeah, how matter or material respond when we give a certain value of heat, yeah. And as we know that the first thing that we can get, yeah, by giving certain amount of heat, yeah, to matter or to material is that the temperature uh, will be higher, yeah, compared to when we do not give any heat, yeah, to the material. But it's only just a physical aspect of the response of the matter when we give um, heat, yeah. But actually there are a lot of physical aspect that can be understood, yeah, by learning about this thermal behavior when subjected to certain amount of heat, yeah. Okay, so before we start, yeah, our lesson today, I want to give you a brief explanation of matter, yeah. Okay, so in our, as far as we know, yeah, there are three kinds of matter, yeah. The first one is solid, and then the phase of matter, yeah. Phase of matter, solid, and then liquid, yeah. Solid is S, and then liquid is L, and then the last one is gas, yeah, or G, yeah. Okay, so actually there are the four types of phase of matter. It is called with uh, plasm, yeah. But in this case, we are not going to uh, discuss about this one because this is too far, yeah. If you want to, not too far, but actually it is not our focus of study, yeah, because plasma is something called more will be discussed in science faculty, yeah, because our faculty is engineering, yeah, and the department of mechanical engineering, so we are not going to learn much about this plasma, yeah. So we are going to deal with these three kinds of matter, yeah. We have solid, liquid, and gas. Okay, so let's talk about the first matter. So we are going to learn about gas, yeah. Okay, in the gas concept, yeah. Uh, in the concept of thermodynamic, we know something called with the ideal gas law, yeah. So there are word ideal here, yeah. So why we have to put the ideal word, yeah, in this law? Because um, in real situation, yeah. Okay, so this is the um, if we have ideal situation, then it must be we have non ideal situation, yeah. And it is important for us to learn, yeah, about the ideal one, because when we know the ideal condition, when we are faced or when we meet the situation in non-ideal situation, then we can make comparison. Yeah, let's say ideal is something called ideal is some people say that ideal condition is a 100% of situation. Yeah, and when we have non-ideal, let's say from the calculation we got, let's say, 45%. Yeah, then we know that how far, yeah, the non-ideal situation if we compare it with the ideal situation. So if the ideal situation say that the situation is 100% and in non-ideal is 45%, then the difference, yeah, between this one and this one is at least 55%. Yeah, so we can make so we can consider how far, yeah, the real situation when we compare with the ideal situation. Yeah, and in this semester, yeah, we are going to learn much about the ideal case. Yeah, because the non-ideal case will be learned, yeah, in other semester, but because this is the basic knowledge, yeah, of physics, then we will focus on ideal situation. Yeah, okay, so this is the ideal case law. Okay, so I will make it simpler. So actually you can there is a passage here, and if you want you can learn it by yourself, but I will put the important things, yeah, so we can just shorten our time, yeah, and make it more and make it simpler. Yeah, okay, so as you can see, yeah, on the screen there is an equation of ideal case law. Yeah, so in ideal case law, yeah, in ideal case, yeah, in ideal case, yeah, the physics properties of gas is depend, yeah, is dependent is based is depend on uh, three things. Yeah, the first one is pressure, and then the second one is the volume of gas, and then the third one is the temperature. Yeah. And by using this equation, then we can know one of the um, things. Yeah, one of the thing when we have already know the other two. Yeah, let's say if we have already know the data of the gas pressure and the volume, then by using this ideal gas law concept, we can know the temperature. Yeah, and if we know the volume and the temperature, then we can exactly know the value of pressure. Yeah, and also if we have already known the pressure and also the temperature of gas, then we can directly uh, find, yeah, the value of volume of the gas. Yeah, so in ideal gas law it is very simple. Yeah, because we only consider the three aspects. Yeah, pressure, yeah, which is P, and then volume, which is V, and also temperature is T. Yeah, big T, yeah, not little t, because little t is time. Yeah, but for the big T it is temperature. Yeah. Yeah, okay. So let's talk about this formula. Yeah, so I will rewrite this equation: P V N K T. Yeah, okay. So what is P? Yeah? P is pressure. Yeah, so P is pressure. Yeah, so this is pressure, and then V is volume, and then T is temperature, Okay, so what is k? Yeah, so k is constant. Yeah, so it's constant. So key, the value of key is this 1.38 times 20 to the power of minus 23 joule per Kelvin. Yeah, so k is 1.38 times 10 to the power of minus 3 joule Kelvin. And because this is the constant, so it's better for you to memorize this, yeah, or remember this, yeah. And this constant called with uh, Boltz, Boltzmann, yeah, Boltzmann, okay, double N constant. Yeah, so Boltzmann is a scientist, yeah. Also, the physicist comes from the Austrian, yeah, and he lives in 1844 until 1906, yeah, 1906, yeah. And due to the to give the honor for this person because he found this constant, so people put his name on his constant, yeah. So Boltzmann's constant, yeah. Okay, and well, how about n? Yeah, so the n here is number of molecule. Yeah. Okay, so number of molecule, and yeah, as far as we know that in very small container, yeah, and it contains gas, yeah, the number of molecule is so big, yeah. So this number of molecule can be billion, yeah, or it can be 1,000 billion, yeah, because it is very big, yeah. Okay, but in but yeah, the equation of ideal gas law is not only this, yeah, because we have the alternative, yeah, because we have the alternative equation, yeah, and it is the modification of this equation, and this is the alternative equation, yeah. Okay, I will little bit discuss about this. Okay, so uh, the first equation of ideal gas, yeah, is like this, right? PV, yeah, equals to NKT, yeah. Okay, so this P and this V. Now, I just want to remind you about the concept of Avogadro number, yeah. So this is the Avogadro number, yeah. And if we talk about Avogadro number, then we have to also, yeah, mention about the concept of moles, yeah, of gas, yeah. And um, this is the mole, yeah. And the relationship between mole, number of molecule, and also Avogadro number is like this. So this is the n, which is the number of molecule, and then this is the Na, yeah. So the moles of gas, yeah, equals to total amount of molecule, yeah, of gas divided by the Avogadro number, yeah. Or we can also say the big N, yeah, equal to small n times the Avogadro number, yeah. Okay, so the how is the value, yeah, how much, yeah, is the value of Avogadro number? So in this book, it is already mentioned that the value of Na, or the value of Avogadro number, is 6.022 times 10 to the power of 23, yeah. So the value of Avogadro number is 6.022 times 10 to the power of 23, yeah, number of molecule. Okay, so this n, yeah, can be modified in using this, yeah. Okay, so small n times Avogadro number times k and times t, yeah. Okay, and then we can also modify this equation, yeah, into this one, yeah. I will, okay, so n, it is stay here, so it stay here, the n. Nah, if we multiplied, yeah, the Avogadro number with the Boltzmann constant, then we can find R value, yeah, R value, yeah. So what is R value? So R is, yeah, so R, yeah, so R, yeah, is called with universal gas constant, yeah. So R, yeah, so R is called with universal gas constant, yeah, and the value of R is 8, yeah, 8.314, yeah, joule per Kelvin, yeah. So 8.314 joule per Kelvin. So this is the value of R, yeah. Okay, so until this step, we already have two kinds of ideal gas law equation. The first one is PV equals to NKT, and then the other one, yeah, because we have the mole of molecules, then our equation will be PV equals to N or RT, yeah. Okay, so we already have two equation here. Yeah, this is the first equation, and then this is the second equation. And which one is the best? Yeah, actually it is not the best or not. It depends on um, the problem that you have. Yeah, if the problem mentioned that the data is already known about the mole value, then we can use this one. Yeah, but if uh, the gas, yeah, the property of the gas is already known with its number of the molecule, then we use this one, yeah. Okay, so it depends on what problem you have, yeah. Okay, so I think this is the concept of ideal gas law, and after this video we're going to try to apply our understanding on ideal gas law by doing this example, yeah, the example 17.1, yeah, but I think it will be done in the next video. Okay, so thanks for your attention until now, yeah, and we are going to continue our explanation on the next video. Thank you.